Welcome to today's discussion of our Unit 3 topics, where we'll review pertinent information for our Exam 3 coming up, where we are covering chance variability. This unit helps us get an idea of the way of how the chance process functions in the context of research, sampling, and research methods, and gives us an introductory idea of how we're going to use some of our earlier concepts in modeling samples and modeling populations, and doing, as we will in our next unit, inferential statistics. We start with chapter 16, the law of averages. In this chapter, the main point is that the law of averages is generally tells us that with a large number of tosses, the percentage of heads is likely to be close to 50%, although it's not likely to be exactly equal to 50%. When the error is likely to be large in absolute terms, but small relative to the number of tosses. That's the law of averages, and we saw it illustrated in Carrick's coin tossing experiment, where, as we can see in the figure on the left, as the number of tosses goes up, the absolute size of the average increases steadily, more or less. But when we look at the error, the chance error, as a function of percentage, then you can see that as the tosses go up, the error goes down. And we see that idea echoed throughout the rest of the material for this unit. We remember that a chance process functions because a chance process comes out differently every time. The law of averages doesn't change the chances as you get more samples. This is just a fact of the chance process. The idea of a chance process helps us understand the extent to which the numbers are influenced by chance. And this is a problem that we face over and over again in statistics. And as you saw throughout our unit, this is a theme. And a general strategy that we used in this whole unit was to find an analogy between the process we're studying, and such as sampling voters in the polling example, and relate it to drawing numbers at random from a box, because the box model gives us a nice model for a simple random sampling. Then we connect the variability you want to know about with the chance variability in the sum of numbers drawn from the box. We connect that through the standard error. And when we use this analogy, where a chance process is related to drawing numbers from a box, it's called a box model, and we use the box model over and over to solve problems throughout the unit. The point is that the chance variability in the sum of numbers drawn from the box is easy to analyze mathematically, and we can account for or estimate chance variability pretty reliably. So the first statistic we looked at, the sum of draws from a box, is easy to manipulate mathematically, and it was a nice tool for helping us learn the applications throughout the chapter. The sum of the draws is a key ingredient for modeling the drawing from a box. It is really important how you model your box, as we'll see in a moment. The sum of draws, of course, is just drawing the numbers the tickets at random from a box, and then adding up the numbers on the tickets. When making the box model, you want to ask yourself 3 basic questions. Which numbers go into the box? Is this a box model where the numbers are like the numbers on a die where each number is individually meaningful, and we are interested in the rates of occurrence of each of the numbers in the toss, or as if is it classified in counting, where, for example, we might be only interested in instances where a 6 comes up. So then our box model would be a 1-0 style box model, where any number that's not a 6 is a 0, and any number that is a 6 is a 1. How many of each kind of ticket are in the box? And as we see later, sometimes we know how many tickets are in the box of each kind, and sometimes we have to go backwards and infer from a sample back to the population. And how many draws are taken from the box? This is the main points of chapter 16. To help us build on our box model and give us some more tools for analyzing the model, we then moved into looking at the expected value and the standard error. To help you conceptualize the expected value, remember that a chance process runs repeatedly, and each time the chance process runs, the number delivered by the process are going to vary a little bit around the expected value. And the expected value is based on the composition of the box and the number of draws. The amount that the numbers delivered in a chance process are off are similar to the standard error, and chance process is underlying all of this. So if we didn't have a simple random sample, then we might not have accurate expected values either. To find the expected value, just take the number of draws and multiply it by the average of the box. Next, we learn about the standard error. The standard error tells us how big the chance error is likely to be. And throughout our unit, we learned about several different types of several different applications of the standard error to different contexts. And in this first instance, we are looking at the standard error of the sum of draws. Shh. Thank you. The square root law is an essential part of why the standard error works, and it underlies many or most of the procedures we'll do for the rest of the class. The square root law tells us that when you draw at random with replacement from a box of numbers, the standard error for the sum of draws is equal to the square root of the number of draws. Thus, as the standard error does go up with the number of draws, but only in an exponential fashion, or only in the squared fashion. So it doesn't go up in a linear way, it goes up just by a smaller portion of the number of draws. And that's what the square root does. It helps to adjust for the law, it helps to model what we see in the law of averages. And another reason that this works for the standard error is that there's two parts here, the square root of the number of draws, but also the standard deviation. And the standard deviation measures the spread among the numbers in the box. So if there's a lot of spread in the box itself, the standard deviation is big, and it's going to make it harder to predict how the draws will turn out. So the standard error will be big too. Likewise, if you have a smaller standard deviation, you'll have a smaller standard error and more accurate predictions from that standard error. The standard deviation is for a list of numbers, like the numbers in a box. However, it differs from the standard error, which models a chance process and the variability that you would see in a chance process. So the standard deviation tells us the spread in the numbers. The standard error tells us the chance variability that's likely to occur or likely to be observed. We also learned a very useful shortcut for finding the standard deviation. So we do have to use it frequently in our standard error calculations. And I definitely want to know how to find, well, all these values that we've discussed already, the sum of draws, the expected value, standard error. And you can use this shortcut for getting the standard deviation anytime you have a box with a 0, 1 style, or with a big number and a small number. So there's just two numbers in the box. And then you can apply this shortcut. We see this most frequently when we have a 1-0 box, but you could use it with other types of boxes. Remember, when you use it, that the fraction with the big number is the fractional representation of the big number in the box. You could express it as a fraction or a proportion. And the fraction with a small number is the fraction or proportional representation of the number of the small number in the box, or the number of tickets for the small number. And you see here what we discussed earlier about classifying and counting. Sometimes you've got a box where each of these numbers is relevant in and of itself, like if the box was had a ratio or interval, that had an interval ratio scale variable in the box, then that's what we would see in box 1 here. Or not, we could have other, box 1 could represent other conditions, but if it's an interval 1, then with like a scale 1 to 6, and we could represent it like this, and each of these numbers are meaningful. But there are instances where the numbers themselves are not meaningful, and we just use the numbers to classify, and in that case, you change everything except the outcome of interest to a 0, and the outcome of interest is a 1. After we learned about the expected value and standard error, we built on this foundation to apply these concepts in the context of the normal distribution, and examined how the normal approximation works for probability histograms. Remember that a chance process generates a number, and the expected value and standard error are your guide to where that number will be. So you don't know the exact number that's going to be produced by a chance process. You can just predict it with some degree of confidence, as we see. And we can use the probability histogram to give us a complete picture of this. Our probability histogram represents chance, not the data itself. So unlike an empirical histogram, which represents data, our probability histogram is just a representation of the chance processes and the probabilities that you can use for modeling that variable. The chance is represented by the area under the curve, which we can divide up using the standard unit scale. We'll look at a couple examples here. As you see, that this is an empirical histogram because these are the actual data observed in 100 repetitions of tossing 2 dice 100 times. And as you can see, that with just 100 repetitions, we don't have a normal curve. There's maybe a trend there, but as you can see, when we increase the number of repetitions, the curve gets, or the empirical distribution, or empirical histogram gets closer and closer to a normal distribution until finally we see it after 10,000 repetitions. It very much resembles exactly the probability histogram. We can use this probability histogram to predict expected ranges and sums for this distribution. The probability histogram gets close to the normal curve as the number of tosses becomes large, but the number of tosses it takes for a particular histogram to finally resemble the normal curve varies depending on the makeup of the box, as we'll see. This is an example of a normal approximation when we're looking at the number of heads observed across number of tosses, 100, 400, 900, and you can see that the histograms follow the curve better and better as the number of tosses goes up. We also looked at the issue of endpoints in the normal approximation, and let's just spend a moment on this to remember that when we have endpoints that are inclusive, that includes the numbers that are listed. So here, if we want to find the heads inclusive, we want to have a range that actually includes these numbers. So we want to go from, for example, 44.5 to 55.5. So we have a range that would include these numbers. Exclusive range might go from 45.5 to 54.5. And as you see here for part A, they illustrated finding exactly 50 heads, because then you want a range that just only includes 50. So here the base of the rectangle goes from 49.5 to 50, or 50.5 to basically from 49.5 to 50.5 is the range that includes 50. And you can see that illustrated on this diagram here. Here's 50. This goes from 49.5 to 50.5. We can model that shaded area under the curve. We can use our normal approximation to find the chance of a expected value, the chance of getting exactly 50 heads in your 100 tosses. And you simply use the normal curve. Shh, please relax, honey. However, we often don't need to go on. As you can see, this is the range that we discussed earlier. It would go from standard score of negative 1.1 to a positive 1.1. And then you could find that by looking in the normal, your standard unit table, and getting this area. Oh, quiet, get out of here, please. However, oftentimes it's not specified whether the endpoints are included or excluded. So you can just go ahead and use a compromise procedure, where if you want the number of heads from 45 to 55 or in that range, you can just use the numbers themselves, and it's close enough. So it's important to remember that the endpoints are an issue sometimes, but it depends on the level of precision you need. We can use the normal approximation quite well with certain data. Some boxes have are more normal and have a more even distribution than others. So as we saw that box earlier with the 1, 2, 3, 4, 5, 6, like for a die, that box is very even. However, if we look at this lopsided box here with 9 zeros and 1 1 in it, here's a histogram for that box, and you can see the histogram itself for just one toss is quite, or maybe for 100 tosses, I don't know. Anyway, the histogram is very lopsided. And when we repeat these, oh, this must be just one. When we repeat these draws, it's still not a very normal distribution at 25 draws, even at 100 draws, and you really have to get up to a high number of draws before the normal approximation takes hold. So if you have a lopsided box, it might not be appropriate to use the normal approximation if the box is very, very lopsided like this. And especially if you have a small sample. So if you have a lopsided box but a really large sample, then it might be appropriate. I mean, then it's probably still appropriate. Like if you have several thousand people or millions of people in the sample, then your sample is going to be big enough so that you can still use the normal approximation. Here's another lopsided box, this 1, 2, 9 box. This histogram is nothing like a normal curve at all. Oh, and here you can see this idea illustrated much better, where at 25 draws, this isn't even at all. It's, this is not a normal distribution. Still far too wavy to be called a normal distribution. Even at 100 draws, you can see there's some wave in there, although it's better. But as the number of draws goes up, it gets better at approximating the normal histogram. Chill. Finally, remember that the normal curve is tied to sums, so you can only use it with calculations that use sums and products. These are examples of some product histograms or multiplication-based histograms, and you can see how it doesn't matter how many rolls you do, they'll never approximate a normal curve. Remember that the expected value and standard error for a sum can be computed from your number of draws, the average of the box, and the SD of the box. We practice this a lot in the next couple chapters, and the expected value pins the center of the probability histogram to the horizontal axis, and the expected value becomes a standard unit of 0, and then the standard error fixes the spread of the distribution. Please, oh my gosh. Then we looked at sample survey issues and discussed how the sampling frame can affect what you see. We highlighted a couple of specific ideas from this chapter. We introduced the idea of parameters, where we've been discussing samples to this point, but a sample is just part of a population, and a parameter is simply a numerical fact about the population. Generally, we don't know the parameters exactly, and they can be estimated, which we learn later we can use the bootstrapping method to do. A statistic is computed from a sample and sometimes used to estimate a parameter. The issue when you're estimating parameters is accuracy. It's not enough to just estimate the parameter. It needs to be accompanied by a confidence interval or a standard error to help you evaluate how close the parameter, how close to the actual parameter the estimate is likely to be. Another important idea from this chapter to remember is that the method of choosing the sample matters a lot, especially as it pertains to selection bias, especially. We also discussed non-response bias. But selection bias is a very important one to keep in mind when you're looking at examples of research and, for example, sampling scenarios on the exam. You want to be thinking about, is this a simple random sample? Is there selection bias here? Because that's going to tell you whether or not you can use all of these techniques that we're learning in this unit. Finally, the best methods of sampling always involve the planned introduction of chance, hence our emphasis on the simple random sample, which uses probability in sampling. So we discussed bias, and when you're appraising a sample, as I said, ask yourself, what's the population and the parameter of interest? How was the sample chosen? Is there selection bias? And what was the response rate? That's to help you identify non-response bias. And a large sample is not going to protect you from bias in any way. It's just a bigger bias, or a bigger, a sample, a bigger biased sample. So we use chance to help us do good sampling. The probability methods for sampling are objective, and the objective process is the chance process is random and leaves no discretion to the interviewer. Anytime you leave discretion to an interviewer, you're going to see selection bias, period. So if you're reading a problem and you see something where the interviewer gets to make a choice about who is in the study or not, or anyone else along the line is making individual decisions, that's bias. And it's not a simple random sample. So how well do these probability methods work? They're pretty good. Bias is very problematic in studies. We have to work to minimize bias all the time. Even if you're thinking, well, wouldn't it be good to know the selection bias? Well, of course, it's good to know the full selection process for your study, but knowing the bias doesn't protect you from the effects of the bias in your study. And so selection bias in your sample will color your results, and it really negates the use of many of the techniques we discussed, especially bootstrapping, be completely inappropriate with anything but a simple random sample, and your standard error estimates are destined to be probably or potentially very far off. This is because anytime there's judgment and choice, it inevitably shows bias. We can't help it. And that's why we use these probability methods, because chance is impartial. So we talked about how the estimate is comprised of the parameter plus whatever bias is present and chance error, which is always there. Remember that chance error is sampling error, because that chance error is in the sampling process. Remember, the random sampling is the chance process. Bias is called non-sampling error because the bias is, although it might impact the sampling, it's not something that you can account for using our sample modeling techniques. Oh my God. So we quantified our chance errors in sampling, and we're back to the expected value in the standard error. When you have a simple random sample, now we can say, okay, if we have a simple random sample, then it's fair to assume that the expected value for the sample percentage equals the population percentage. However, the observed sample percentage will always be off due to chance error. So you can model the percentage in the sample by finding the percentage in the population and adding chance error as interpreted in the standard error. To compute the standard error, please. So to compute the standard error for a percentage, you just use the same process you did to get the standard error for a number, like a number of draws, and divide it by the size of the sample and multiply by 100. And this gives you a per 100 standard error that we can use in a lot more contexts than we could the standard error for the number itself. We learned about this correction factor for times when the sample is a very large part of the population. So when the absolute size of the sample determines the accuracy of the percentage estimates as long as the sample is only a small part of the population. When the sample is large relative to the population, then you have to use the correction factor to adjust your standard error. I wouldn't worry about it too much. You should be aware of the correction factor, but it's not like a computation I'm especially concerned about for your exam. Remember, the sample is only part of the population, and you should always use a box model to help you find the standard error. Remember to adjust your box if you are given, if the problem asks you for something classifying and counting, remember to adjust the box as necessary, because the 0, 1 box can be a lot more convenient to deal with. In our next unit, we look at how to move from the draws and the sum of draws into some more useful statistics that we see more frequently, like the percentages and averages. So next we looked at the accuracy of percentages. And here we learned the backward method for getting the population estimates, aka the bootstrap method, where you estimate the population parameters using the information from the sample. We also looked at how when we use the bootstrap method to infer population parameters, we need to give a standard error, or we need to give a confidence interval with our population estimate, and our confidence interval is generally 95%, which is plus or minus 2 standard errors. It's important to remember with chance error, there's not a sharp dividing line between what's possible and impossible. We can just speak in terms of what's likely or unlikely, being reasonably, per certain percent confident. You could really find any different confidence level, but 100%. We can never be 100% confident of an estimated population parameter. So we also talked about how, again, the simple random sample is the key idea here, because it embraces the chance process, and it's modeled by can be modeled by a box model. So you can only use all of these formulas for when you have a simple random sample. If you don't have a simple random sample, the formulas may not apply, and that's something to keep in mind when you're reading through scenarios for the exam or on the exam, this one and the final, because sampling has been a major theme of our class and this idea of the simple random sample. When we use a simple random sample and bootstrap to estimate the population percentage, our percentage estimate is always off of a little bit off the population percentage due to chance error, and standard error of the sample percentage gives us the likely size of the amount. It's fine to bootstrap when the sample is large, but if you have a small sample, bootstrapping is not appropriate. And a confidence interval is just an application of the standard error and very useful when you're estimating a population parameter. In our next unit, we finally look at the application of these very same techniques, but with averages now. So instead of looking at the sum of draws from a box or the percentage of draws, percentage of the sum, we'll look at averages, which we're quite used to seeing in journal articles and other places. The average is very useful metric, measure of central tendency, and it's one that we will use quite extensively in our next unit on inferential statistics. So this chapter 23 material we're going to certainly be carrying forward in our next unit. We basically get two more applications of the expected value and standard error. Now the expected value for the average of draws and the standard error for the average of draws. The expected value for the average of draws is pretty easy to get. It's the average of the box. The standard error, also easy to get, but you have to first get the standard error for the sum and then divide by the number of draws. The standard error we've looked at in lots of different contexts, and it's important that you remember to use the right standard error at the right time. The standard error is always going to show you the likely size of the amount off, but depending on the context that you are in the type format of the statistic that you're looking for, you might use one or more of these standard error computations. So when we are reasoning forward, because we know the composition of the box, the population, we know everything we can about the population, then we can just compute the standard error exactly from the composition of the box. But when we're reasoning backwards, we need to estimate the standard deviation of the box from the sample and then get an approximation of the standard error. And just simply remember to pay close attention when you're reading problems to give your answer in the right format. If you're asked for standard error percent, that your answer really does need to be provided in percent format this time. If you give me a different standard error, that's a different formula, that's a different answer, and it's not correct. So please read carefully and make sure that you're using the right standard error in your calculations or in answers that you submit. Remember that sampling, just one final reminder about this simple random sample. Just because you're given data doesn't mean that it's appropriate to do certain calculations on it. You can always carry out arithmetic, but math is not going to protect you from bad methods or poor logic in applying the correct procedure. That's why it's so important to remember first thing when you're reading a problem is to say, okay, is this a simple random sample if it's a research scenario? If it is a simple random sample, then you can go forward with the calculations we discussed in this chapter. If it's not, then that might be an instance where you need more information, or there's, it's not possible to compute. A popular kind of sample that's not random is a sample of convenience, which is whatever's convenient to the researcher. It's not chosen by a probability method, and so you really can't use these estimates, these statistics on it. So that's a quick overview of the basic concepts in Unit 3. As far as the exam material goes, you definitely should know how to do the expected value and standard error calculations for the different scenarios that we looked at in this chapter. When you're looking for example, the sum of draws or the percentage or average estimates. Make sure you're familiar with and comfortable with all those calculations and the process for applying the normal curve to in the context of these models, so you can use them to estimate the probability of various scores or areas under the curve, ranges of scores. Confidence intervals are another important topic. So as it's just a common application of the standard error. Remember, especially confidence intervals are only appropriate with a simple random sample and really a large sample, the two. And if you want to do extra practice problems for the exam, which I highly recommend, I strongly recommend taking a look at the even items in chapter 20, which was our chance errors in sampling. Really all the items in the chapter 20, the exercises and the review exercises, have many nice examples of items that will give you good practice with the kinds of problems that you could see on the exam. The items in the later chapters, 21 and 22, are also really great. The items in the earlier chapters from this unit are good, but the reason I especially like the items in chapter 20 is that they give us context where we apply the material from the earlier chapters in context. So chapter 20 really brings it together, and there's some great items in there. So I would recommend doing those even items and taking a look at those. And also take note of the special review exercises that are at the end of chapter 23. Now, the exercises in this area do cover all other units, and the material on the exam could cover other units too. But the ones that I thought were especially pertinent to our current unit were in particular items 1, 2, and 3. And then the later items starting at about item 17. And really the items from 17 through 30 do apply to this unit. I especially liked the items from 24 through 24 through 30. Those are some nice, great example items for you to practice. So The special review exercises, I always recommend doing them. I'll tell you what, I always take items from the special review exercises and include them in the exam. And the even numbered exercises are also great fodder and often will show up in exams too. Again, especially chapter 20 and then 21 and 23 too, because you want to make sure you feel comfortable with those formulas and those applications. Even though those chapters were brief, they are really important for our future applications. So good luck with your exam, and may the odds be ever in your favor.